So the following is an introduction to using Python arrays and also plotting. In order to begin, we need to use the numpy library, as most of the functions that we use with arrays will be from the numpy library. To use this, we type import numpy as np, and then all the functions will be np dot whatever function we have. Python has some built-in arrays, but we're just going to use numpy and be done with it, since they're much more flexible and powerful in numpy than in regular Python. There's a number of good links here that you can click on to find more information and tutorials and whatnot. We create arrays in numpy by typing x equals, for example, x equals np.array, and then the array is a function, and we give it a list type inside the parentheses. And to indicate an array, arrays are going to go inside square brackets, so 1, 2, 3, 4. So it's a comma separated list of elements between square brackets. You can think of an array as a collection of variables or a vector. So in math, we're familiar with this concept of a scalar, which is a single number. We can also have vectors, which are collections of numbers. And in this case, we would have a four-dimensional vector, or we call this an array with 4 elements in it. This is convenient if we have large sets of data and we want to treat them as single objects. And this would be analogous to like a column of data in Excel, where we have a number of values in each cell. We can make two-dimensional arrays. A two-dimensional array is like a 1D array, except each element is itself an array. So here you can see the outer square brackets, and inside the first element is an array, so bracket 1, 2, and bracket, and then the second element is another array, bracket 3, 4. And when we print it, we get this two-dimensional array. We can create an array using the arange command, which is the analog of the range function. We type np.arange 3, 21, 3. This behaves just like the range function, in that this means we'll go from 3 up to 20 in steps of 3. We can create a two-dimensional array by using by reshaping a one-dimensional array. So in the above example, np.arange, we can the result of this command, np.arange, is an array, and so we can operate on that array by typing array.reshape 3, 2. We can create an array of zeros that are of size 6 by simply typing np.zeros. This is great for initializing. You can also use np.empty. It's supposedly faster to create because it doesn't have to initialize the values to anything. So you can see this just creates an array of zeros. You can make an array of ones, like array np.ones 6. That'll create an array of 6 ones. And that's useful if you want to initialize an array to have all the same values. So if you type x equals 5.0 times ones, np.ones 6, it'll create an array of 6 elements, each of which have the value, with each element having the value 5. Another great function is linspace. Linspace will go from 2 to 8 inclusive, with 5 points. So you'll have 5 evenly spaced points between the numbers of 2 and 8. And in this case, both 2 and 8 are included in the list. These don't have to be integers. Well, the number that you use would be an integer, but the starting and ending values don't need to be. So we use this all the time. So for instance, if we want to create a list of times between 0 and some value, we'd use linspace, for instance, just a linear spacing of values that increase in time. Okay, so that's how to create arrays. Several different functions that we've shown, and there's others available, but these are the main ones that we'll use. we can access elements of an array using square brackets with an index number. Array indexing always starts at 0. So if I have an array, x equals np.a range 3, 21, 3, then the value of x is shown on the right, and the indices that correspond to those values are 0, 1, 2, 3, 4, and 5. If we want to access element with index 2, we type x square bracket 2, and that will return 9, which is the value corresponding to index 2, again starting at 0. If we have a two-dimensional array, in this case x is a 2D is a matrix 0, 1, 2, 3, we access it again with brackets with commas. So this would be like x element, this would be row 1, column 0. So we would get this row 1, column 0 gives us value 2. So this has the same notation that we use in linear algebra, a, I, j, where I is the row and j is the column. Here we have an example of how to access arrays using array slicing, as it's called. Suppose we have the array x that we used above. If we print x with brackets colon, the colon means everything. So it's going to access everything in x. We could also just type print x without the bracket colon, but the colon means everything. If we do 2 colon, that will grab index 2 up to the end of the array. So it'll get everything from element 2 to the end. If we go 2 colon 4, that will get indices 2 and 3, skipping 4. So that behavior is similar to what we've seen with the range function. We can also go backwards from the end. So x minus 1 will give us the last element in the array. Minus 2 will give us the second to the last element in the array, etc. So you can count backwards using these negative indices. And we can also use an array of indices to access which elements we're interested in. So in this case I want x and then bracket, and then I have an array which is 1, 2, 5. This will tell me get the values in indices 1, 2, and 5. And you can see we get 6, 9, and 18. So 1, 2, and 5 give us 6, 9, and 18, and that's what's output. So this can be especially handy if we want to access particular values in the array. Suppose we have an array of positions like x, and we want to find the array of differences between consecutive points. So here I have an array called x, and it varies from point 1 to 7. There's 10 elements in the array, and I want to find the difference in positions between subsequent elements. So I want to know the first element in the dx array would be 0.2 minus 0.1, and the second element would be 0.4 minus 0.2, and the third element would be 0.8 minus 0.4, etc. One convenient way to do this is to type dx equals x 1 colon minus x 0 colon minus 1. So this will grab 1 to the end. We'll make an array out of all of these points starting at this value 0.2, and then we're going to subtract from that all the points from 0 up to but not including the last. So that'll go from 0.1 up to this one. And when we line those two up and subtract them, we get and store it in an array called dx. Then we have the array of delta x's. So rather than having to go through and make a for loop where we evaluate the difference each one at a time, in this case we can just do a simple one-liner using array slicing to say take the difference between these points and these points. And of course dx will have 9 elements instead of 10 because there's only 9 differences between 10 points. Another way that we could do this is simply assign the indices of interest to a variable. So here I have an array of indices that go from 0 to 9 and an array of indices that go from 1 to 10, and then I can write dx is equal to x of the I plus 1 indices minus the array of indices xi. And this will do the same thing as above, which can also be convenient. In both cases, we get dx shown, and the same values are output when we do this approach and this approach. We can find the shape of an array using np.shape, the shape function. For a 1D array, the shape function is a tuple of values. In this case, it's just 10 because it's a 1D array. We can also ask for the size of a 1D array, and that'll tell us how many elements are there. The len function is also available, len, and that'll tell us that the size is 10. So this is very convenient. If we have a two-dimensional array, we can use the shape function, and notice that the shape of the two-dimensional array is the number of rows and the number of columns, so 3 by 2. The size function, though, in a 2D array doesn't give us the length, it gives us the total number of elements, so we get 6 instead of 3 or 2. But the shape function will return 3 and a 2, and this is like an array, it's called a tuple, and you can access either element 0 or element 1 to figure out how many rows or how many columns there are. So np.shape, this part returns a tuple, and then the 0 means give me the first element, and the 1 means give me the second element, so I can recover 3 or 2. Operations are done on entire arrays, which is very convenient. So I can just type, if x is an array, I can square the whole array element-wise, and I get x squared will square every element. So 3 becomes 9, 36, 81, 144, etc. as shown here. So this app is very convenient, much more convenient than writing a nested for loop over each row and each column. If we multiply two arrays together, so y is minus 2 times the x array, then we can multiply these things together, and again it multiplies them element-wise, which is very convenient, much faster than the corresponding code in languages like C++, for example. We can take the dot product of two vectors using the np.dot function. So if x and y are two different arrays, np.dot will take the dot product. This is equivalent to typing np.sum of x times y. So x times y will multiply each element, and then sum will sum all the elements up, and the output is a scalar, as expected. We can use ax equals b systems to solve, or we can use these arrays to solve linear systems of equations. So if we set an array A, which is a 2D matrix, and an array B, then we can solve x in the ax equals b system using the np.linalg.solve function, and we just simply pass it a and b, and it outputs the array x. And if we like, we can test to see that we recover b when we type dot product of matrix A and vector x, and we recover, when we do that, we recover b, which was our b array. It's very important with arrays that you're very careful about assignment. Python's a little different than many languages in this way. For example, if we have x equals an array 1, 2, 3, 4, and we type y equals x, you might think that we have a completely separate array called y that also has the same values as were in x. But we can see in the following code that if we change one of the elements of y index 3 is 44, and then print x and print y, both of the arrays changed, not just y. So x is 1, 2, 3, 44, and so is y, even though we only changed y. And this is because when we assign y equals x, we're just giving the underlying object, this array 1, 2, 3, 4, another name. And when we go y equals 3, we're changing the same object that both y and x point to. This is often not what we want to have happen. So in order to avoid that, we would do y equals x.copy, and that would make a completely separate object for y than x. And then when we type y equals y3 is 44 and print x and y, we can see that x is not changed, but y is, which is usually what we want. There are tons of other functions available, and you can see the links at the top of the document. There's repmat, which will make new arrays out of existing ones, repeat matrix. There's hstack and vstack, which are very convenient for combining arrays together. There's sort, diag, transpose, etc. Many other functions that you can browse through that are available. So plotting in MATLAB, this is a little different. In order to plot in MATLAB, we need to import the relevant libraries again. And this library that we import is called matplotlib.pyplot, and we import it as PLT. So this will allow us to use all the plotting functions as plt.function name. And then if we're using the Jupyter notebook, this line %matplotlib inline is also needed. That's just a way to make our plots show up. So this little bit of boilerplate here. Suppose we have a function, an array x and a corresponding array y. A very simple plot is to type plt.plot x comma y, and it outputs an xy plot. Very simple. Now we normally want to format this up a little bit. We'd like to be able to change the font sizes. We'd like to be able to add some axis labels and maybe a legend, and we can do that as follows. And maybe change the line style. plt.plot xy, and then this string ko dash. This is the line style. The K means black, the O means symbol, and the dash means a solid line. So if you just wanted symbols, you'd leave off the dash. If you want a different color, you'd change K to something else. And if you wanted a different symbol than circles, you'd use a different character here. Other colors are BRGCM for blue, red, green, cyan, and magenta. And there's other line styles, a dashed line, a dashed dotted line, and a dotted line. The colon's a dotted line. And other symbols, a dot, a square, a triangle, a downward triangle, a star, diamonds, and other values, x's and pluses, and left triangles, right triangles, and other kinds of shapes that we can put in. We can give it a label with plt.xlabel, and then a string telling us the value, plt.ylabel, and a string telling us the value, and a title, plt.title, some title. And this is what gets output. So you can kind of format your chart as wanted. You can draw multiple curves on the same plot and do some other things. If you want multiple curves on the same plot, you simply call this plot command more than once. And in this case, we can add the optional argument label equals to tell it a legend for what we want to call the curve. So in this case, we can change the y scale to be log. plt.yscale is log, so that it'll be on a log scale. We can have curve 1 and curve 2 defined with the label. Here we have a black dashed line and a blue solid line, and those show up. We can even put Greek symbols into the X label using latex style code. This R here is an important keyword, so R quote with symbols, and then this $/alpha _s /beta up s, and you can see what the result of that is. And we can even change the font size that we use. This top command, plt.rc font size equals 16, tells us that we want everything to have a font size of 16. So you'll notice some of these fonts are pretty small. This will make all the fonts 16, and then in a couple of places here I've changed the 16 to be 20, so they're even a little bigger, these two legends. To tell it that we want to include the legend on the plot, we type plt.legend, and legend can take a couple of options, like where you want to put the legend and whether or not you want to draw a frame around this little box around the legend. We can get an axis handle if we type ax equals plt.gca. GCA stands for get current axis, and then once we have an axis handle, we can add other functions like ax.set x limits, ax.set y lim, and these are an array telling us what the limits both in x and y should be. So you can see this isn't quite as straightforward as using something like Excel where you just double click and tell it what values you want. The power, however, is that you have full control over this and can make as many plots as you want using once you've set up the code, and can have these done automatically, which can save a lot of time. Not really saved a ton of time if you if you're only doing one plot, but if you're doing tons of plots, that might be a good thing to do. And most of this syntax here follows that of MATLAB. That's why the library is called matplotlib. It's because it's patterned after the kind of syntax that's widely used in MATLAB. We can make a table of plots using the subplots command. In this case, we use the command plt.subplot. The 2, 2, 1 says set up a two row by 2 column table of plots and make the first one the active plot. So this indexing doesn't start at 0, it starts at 1, consistent with with MATLAB. So this is plot 1, 2, 3, 4. So right now plot 1 is the active plot, and so any commands that follow happen on this plot. Then we go over to the next plot, subplot 2, 2, 2. Now this is the active one, this final 2. And then any commands apply to this plot. Here I've added an X label, and then 2, 2, 3 and 2, 2, 4. And then occasionally the output will not look good because these labels will overlap with the plot. So if you do the plt.tight_layout, it kind of makes the plots a little more pretty. You can customize any and all things relating to these plots, where they're placed, how big they are, etc. And matplotlib is a very large library with tons and tons of customization options. Finally, we can make 3D contour plots. So it's a 2D plot, but the coloring represents a third dimension. And the following code here illustrates how to do that. So here basically I create an array of x's, an array of y's, and then I turn those into matrices of x's and y's, so I get the x value at every single point in the grid, the y value at every single point in the grid, and that's done using this handy function called meshGrid. And then I can find the z as a function of x and y at every point by using, in this case, this handy function that makes a pretty plot. And then I can, in this case, I've made a subplot that's 1 row by 2 columns, and I've made a contour plot x, y, and z with 20 contour levels shown. And then I have a filled contour plot, so instead of contour, it's contour f, x, y, and z, again with 20. And then I can put a color bar on there.